This lecture will look again at an application of Markov chain Monte Carlo, but in this case to a problem with a hierarchical prior. This example represents a way to evaluate a number of binary outcomes and compare them using a rather sophisticated Bayesian analysis. And the specific example is one that's called therapeutic touch. And in this case, we have healthcare practitioners who claim that they can sweep their hands over a patient's body at a distance of 5 to 10 centimeters and sense whether and where the patient has depleted energy. If depletion is found, the practitioners then attempt to repattern the patient's energy field. And of course, they charge for this service. So in this study, 28 practitioners agreed to participate to see if the technique is really effective. And a therapeutic touch practitioner in the study held out both of her hands, palm up, with view of her hands blocked by a screen. The tester randomly put her right hand over one of the practitioner's hands, and the practitioner had to say which of her hands was near the tester's hand. So it was a way to see if the practitioner can actually feel the energy of the tester without seeing where the hand of the tester was placed. For each therapeutic touch practitioner, they had 10 trials. If the practitioners are guessing in this experiment, then they would get on average 5 right. And if they are in fact able to really sense the energy in the tester's hand, then we would expect them to get some number higher than that at a statistically significant rate. So that's the purpose of the test. So to evaluate the results from the test, we'll use a Bayesian approach using what's called a hierarchical prior, and we'll see how that works here. So we start by assuming that all practitioners come from a common group trained in this practice. And this, in fact, is a good assumption because that's true, that they are all trained centrally for this practice. So that means that we can assume a common group mean, and we'll designate that mean as omega. We'll use a flat prior for the group mean. So we're going to put a flat prior on omega, which is a beta 1,1. And as you recall, beta 1,1 is flat. The dependence of individual abilities on the group we're going to model using the parameter kappa. And that will allow us to see, for instance, if the training that these individuals have received has carried over to them, or so that they all behave roughly the same, or if they basically spread out and become individualized in their ability to do this practice. So for kappa, we're going to assume a mean of 10 and a standard deviation of 10, which will allow for variation among practitioners. So we'll apply sampling to get an estimate for all of the theta j's, where the j represents each one of the 28 practitioners. So theta then is the probability the practitioner correctly guessed whether or not the hand was in the right place or not. So this is a 0-1 response. And theta j then is the probability that they got the 1 or the correct answer. So here's what our graphical model looks like. And again, we're going to use a Kriska diagram to describe it. Starting at the bottom again then, our likelihood is Bernoulli, and we have 28 of these. So each outcome then is 0-1 for each one of the practitioners. We're going to model the parameter in the Bernoulli, the theta, by a beta. And as we said, we're going to model that beta using these values omega, which is the mean, the group mean, and kappa, which is a measure of how strongly we believe that group training is applied to each individual. The kappa then will have a gamma distribution because, again, it's bounded below by 0. And the omega will have a beta distribution. And as we said, we're going to actually apply a flat beta. So effectively, it's a uniform distribution between 0 and 1. All right, let's now look at the code. All right, so we again load the necessary Python packages, and we also note that we've got the link there for the code and more code that's like this. So you can go and see additional results, and you can see additional results on this particular example as well. And then we load the data. Again, you have to enter your own path for where you've got the data. And you can see that when we look at these data, we've got the response, y, which is 0, 1, and then we've got a categorical variable, which is just giving us the designator for each one of the 28 practitioners. We can look at the proportion of correct answers by the practitioners, and you can see that it ranges from almost none right, 0.1, to quite a few correct, 0.8. So the practitioners are spread quite a bit over the range of possibilities in terms of their performance. And here's a graphical model. As we said, we've got the response is Bernoulli. We have a beta prior on that on the theta for that response. We have an omega, or excuse me, a beta prior on the omega within the prior of the beta, and on the kappa we have a gamma prior. And as we just saw, here's the Kruska graphic. Again, we put it here for purposes of making sure that we can find it in our Jupyter notebook. All right, here's the run of the model, and we can see that again we've got good convergence on all fronts. The omega and the kappa both show good convergence. The kappa, of course, is showing what we would expect, which is a skew in it because it's bounded below by 0. But it's converging in terms of its performance, and the same thing is true of the omegas. The thetas, you can see there's 28 of those parameters in there, and we can see that there is some variation, but they seem like they are actually all pretty much converged in around one area, and unfortunately for them, that happens to be 0.5. We can see this even more clearly when we look at the table of each one of those values from the trace, which summarizes the values from the traces for the Markov chains. And this shows it for each one of the 28 practitioners. Notice the highest posterior density region between 2.5 and 97.5. And you'll see that every one of these practitioners bounds 0.5. Now, actually, the ones that are the lowest, interestingly enough, which is to say the ones that do the poorest, are the ones that, for example, let's take theta 0, only write about 35-36% of the time. It's closest to not bounding 0.5, but this practitioner still does bound 0.5. Every one of them bounds it. So basically, we can't reject the hypothesis that every one of these practitioners is essentially guessing the answer as to where the hand of the tester was in this particular test. We can also look at a plot of these practitioners and see how correlated they are to see if there is any notion that they've got some correlation between themselves. And we can see when we look at that, this is just looking at 3 of them, that there effectively is no correlation. The 3 that we looked at was the first practitioner, theta 0, the 14th practitioner, theta 13, and the 28th practitioner, theta 27. And you can see that they all look effectively like they're evenly distributed. And the result is that they are not correlated much with each other in terms of their performance. So this result shows how you can use Markov chain Monte Carlo then for the more sophisticated problem of a hierarchical prior distribution.